Hello and welcome. This is the eighth and final section in Chapter 15 on damped oscillations and resonance. And this includes another feature about simple harmonic motion where we are actually including a external force. All the other examples previously, even the most recent one of a damped oscillation, are considering the motion of the system on its own with its own conservative forces, gravity or spring force, and constantly transferring to kinetic energy. Of course, in the damping case, that mechanical energy gets transformed into the thermal energy of the atmosphere and the system itself. Things get slightly warmer, but all those are instances where the system is completely on its own. There's no other external forces present. And so the problem of driven oscillations, this new terminology here, a driven oscillator is one that has, it's an oscillating system that has an external force applied to it. And you can think of some simple examples that aren't very helpful. If you say apply a constant force to a mass, that where the acceleration and the position are related, if you include a constant external force, then you don't really find much interesting new phenomenon. What does become interesting and what becomes a source of what we call resonance is when the driven oscillation itself is actually, when the force external to the oscillator itself is actually oscillating. So if you have a force that's oscillating applied to an oscillator, then you can get some really interesting behavior. And so we see this picture here of the instrument being able to break the fine goblet. There's plenty of videos out there where you can see that. I'll explain that in a couple minutes, but basically the setup is you can include damping or not in this case. If you ignore damping, then the results can be quite catastrophic if you oscillate it at the specific frequency. So we're going to look at a graph here of a graph of amplitude as a function of frequency, external frequency. So this is a different graph than what we've been seeing. What it shows us is that, for instance, if you take a mass on a spring and if you wiggle it very slowly, let's say you're holding the spring and the spring is a vertical spring and it's got a mass attached to it at the bottom. Okay. You can obviously imagine wiggling your hands to make the spring mass on the spring wiggle. What this graph is saying is that if you oscillate, if you wiggle your hands very slowly, very, very, very slowly, then the mass will more or less respond by not oscillating. It'll move with your hands, but it won't oscillate on the spring. And surprisingly, it turns out that if you wiggle your hands really, really fast while you're holding the spring, it turns out that the response of the mass is similar. That is, it doesn't really move when you wiggle it very, very rapidly. But as you know, there is a sort of a middle ground to where if you wiggle it at just the right frequency, you can get it to start moving. And that's called resonance, where the amplitude of the oscillator grows according to the rate at which you're wiggling or at which you're driving the oscillator. A couple other remarks. If you're somewhere in the middle, it's not too low of an oscillation, but it's not quite at this, what we call resonant frequency. What will happen is the spring will the mass will start to oscillate and then it'll stop. And then it'll start to oscillate and it'll stop. And then it'll start to oscillate and then stop. It'll start to oscillate and stop. And the closer you get to this magic frequency, the longer the oscillation of the mass will be before it stops. Like it'll start oscillating for a while and then stop, and then start oscillating for a while and then stop. And those are called beats, by the way. The book talks about it in chapter 17 in the context of waves. But yeah, as you get closer and closer to the natural frequency, the duration between when it's oscillating and then stops becomes longer, and the amplitude becomes bigger. And so we see in this picture, there's different cases of how close we are. Well, different dampings. When we include damping, the lower the damping, the higher the amplitude. And technically, if you, again, this is another problem that's best analyzed from an advanced course with some differential equations. But as the damping goes to zero, the solution that you get to the equation is that the amplitude becomes infinite. Now, what does infinite mean in this context of an infinite amplitude? I mean, it just means that you're going to be breaking stuff. The oscillations are going to be so large that, like for the mass on the spring, maybe the spring might, the mass might start to vibrate the other way, or if it's like not completely secure, the mass might fly off. Certainly, we understand this from the context of earthquakes. Buildings, you can model a building basically as just a rod standing that's stuck in the ground. And if you shake the ground, if you shake the ground left and right, then the building will also respond shaking left to right. And if you're unfortunate to shake it at just the right frequency, called the natural frequency of the building, then once again, the building will have some calamitous effects. It might fracture, there's going to be damage, it might even collapse. And so civil engineers and those in architecture have to be aware of designing their buildings to be heavily damped near those frequencies that could potentially be dangerous for the building, for the structure. I'm going back to that last example here, or this first example of breaking the glass. Sound, as we'll learn in chapter 17, is an oscillation of the pressure in a fluid, whether it's water or air, or it's a vibration of the lattice in a solid. So in the case of this glass goblet, if you model solids as being collections of balls and springs, well, then those springs have certain spring constants. And so if you, on their own, they might oscillate at a specific frequency. And so if you're able to drive those atomic springs, those atomic oscillators at a resonant frequency, then the energy will be so large, because there's, damping isn't really well defined at the atomic level. You can cause those atoms to break their bonds. And so you can cause things to rip or cause them to fracture. Another example of resonance is how microwaves work. You have to choose just the right frequency of microwaves in order to excite the rotational motion of water molecules. And that rotation of the water molecules is what causes the temperature of the food to increase at such a high rate, to such a high temperature, because there's more energy in the rotating molecules. So resonance is a very common phenomenon in many different areas of science and engineering. Again, mathematically, it's a little bit beyond what this textbook wants to study, but we can always say that the resonant frequency of a system, that is the frequency with which a driving force could oscillate to produce resonance, is always equal to the so-called natural frequency of the system, the frequency with which it would oscillate if it was left to oscillate on its own. And so it'll be kind of a fun example over the next chapters and even beyond into physics 2, where you consider many different physical systems and how in some cases they can exhibit simple harmonic motion. Several examples include floating objects, floating buoys, and things that float in water. If you push it slightly down, it'll bobble up and down. So that's an example of simple harmonic motion. When you get later into physics 2, you can make some systems where these electric charges oscillate, or certainly you can create AC circuits, and light itself is a phenomenon by which something is oscillating. And when you get down to even the basics of matter, even matter itself is oscillating. So this is a very fundamental chapter. Like I said, my first time taking this class, the professor said that oscillation is the most fundamental type of motion. At this time, I would be actually inclined to agree with them. So thanks for your time, and we'll see you at the next chapter. Take care.